Okay. Well, hello and welcome to my contribution paper presentation. My name is Shen Lun. So today the topic I select paper called putting the object back into the video object segmentation. And this is the information that the author and the university and that the paper is accepted in CVPR at 2024. Okay, this is my outline. Okay, that's intro. In traditional object tracking, that the method is to using every unit as a pixel. So using a pixel to matching the next frame pixel, that's to tracking. But it would have the problem of the noisy and the accuracy. So the author is using the new method called the object level memory reading that is using the object as a unit to tracking to the next frame. But it would also still have the problem of the accuracy and the noisy. So the author is using the mask method and the transformer concept to focus on the foreground calculation, which is the blue part of the card. Cat is called the foreground, and the other will be the background. And the pixel will also be extracted to support the object tracking, but not to overpopulation. And in the standard transformer to input the patch of each frame to attention structure, right? So it will need the massive calculation. So the author is also proposed the Qt model with the modified transformer structure and using the object level tracking. So this is the related work that will have the memory base on VOS, which is the video object segmentation, and the transformers in VOS object level reasoning, automatic video segmentation, and all of them is based on the object tracking in the video by using the transformer structure. Okay, now it's the structure that the paper mentioned. Okay, that as I mentioned that we will input the video, right? And the model will separate to each frame, which is the query frame here. It means each frame. And the memory frame, it means that the the model have trained data. It's a sequential, it's have many frames here. And the point of the paper mentioned is the object transformer is in here. That have it's a series structure that so it have not only one transformer structure that have several structure transformer here. Okay. And first that we will explain is the encoder of the query encoder and the mask encoder. Okay, the query encoder is based on the ResNet 18 with the modification which is discarding the less convolution layer and use the Stride 16 features. Okay, and the mask encoder is also based on the ResNet 18 with the modification. Okay, and this formula is the positional embedding formula. As we can see that the S is meaning the object memory here, the data in the object memory here. So it will affect the positional embedding, and we'll talk about this formula later. Okay, and the next component is the pixel memory. And pixel memory is derived from X memory, which is another approach. In the pixel memory, it's basically just store the attention structure needed component, like the keys, value, and the recurrent components with the hidden state called H. And it also have the parameter called affinity, which is indicate that the relationship between Q and K. And in this formula, you simply using the dot product. And the Q is meaning of the encode the query frame to obtain a query feature. So this Q is the feature of each query frame. Okay. And the next is the pixel readout. And as we can see, they have some little relationship to the pixel memory. Okay. And the pixel readout, it's just basically the feature that extract generate by the query encoder. And the FFuse is the trainable small network, and it's based on the previously mentioned that the parameter that A here that's needed, because that's why we have some relationship between the pixel memory and the pixel readout, and combine two of them, and finally we'll get the R0, which is this part, the input of the object transformer. Okay, and that component is called object memory. Okay, and in the object memory, it stores the train frame. Okay, and the U is stand for the object features, and but S is the W is the mask polling weight. Because of previous, we can see that object memory is generated by the mask encoder, so it will have a mask system. Okay, and the U is stand for the object feature that also is trainable by the memory feature. That we can see that the formula here is to normalize the feature by using the mask. And this is the mask definition, that the Q is the index of memory set and the I is the index of each memory set. That meaning the memory structure, object memory structure has many sets, and each state indicate the frame that's trained. So the Q is indicate that which set should select, and the I is indicate that in that set in index of which component. Okay, and otherwise will be the sigmoid function, and it's based on the Fi, which is reverse as mentioned, and the R sign is the positional embedding parameter later, and the F pole weight is also the trainable network. And because that we will input the video right as the data, so the object memory has stored the trained data, so it will be the FIFO system. Okay, and next is the object queries. It stands for the feature that has trained and based on the object memory that can use the weight that to help the model to recognize the specific features. Okay, and for example, that if the object memory is stored each frame, train frame like this, every row. So example that each row is indicate the original image that the object queries will indicate the blue part like this to indicate that feature of the image input. Okay, and the next part is the object transformer, which is the most important structure that the paper mentioned. Then the object transformer is a series structure, right? So it would have be L blocks. L means stand for the number of the transformer. And first of all, we can see the at the beginning we can see that the object queries and the object memory will be summed in the beginning because as I say that the object queries is the feature of the object memory, right? So the size will be same. So we just need to sum in the beginning and let the transformer that know that what have trained. So it can do the further task. Okay, and and the next part is the mask cross in attention structure. That it's very important because the mask cross attention structure is to determine this pixel or object is classified to the foreground or the background. And the above formula is based on the standard cross attention, and the XL is the object queries, and RL is the pixel features, which is here and here. Okay, and the QL is the learned linear transformation of the object, and the KL and VL is the learned linear transformation of RL. And these two parameters will store in the pixel memory. And the author was based on the standard cross attention formula. He added the mask system that to classify its foreground or background. Okay, and this is the mask definition that from above, if the condition is satisfied in here, it will be the foreground, and if it's in here, or it will be the background, or the inverse of finite is meaning that this object is not matching. Okay, so the mask is to control the attention masking, and the query is allowed to 0 or not allowed to inverse of finite to attend to the ITHP sum. Okay, and next is this part. Okay, and as we can see that it's a very standard attention encoder that can communicate each other. Means that we can see the QKV is all as the color of blue, right? So meaning that it can communicate with each other. Okay, and next is the PX and PR. It's the positional embeddings, which is this part here. Okay, and the positional embeddings is defined as the relationship between this term and this term, and in this term is the trainable linear projection. Because of the attention input needed the data to be flattened. So we need to, based on the initial readout, and use the small neural network to let the data be flattened so that we can input in the attention system. And so was the PX. And PR is embedding of pixel, and PX is embedding of the object. Okay, and the object embedding is also the trainable linear projection. That is the trainable neural network. Okay, and next is the FFN that have two kind of FFN in the structure. That called the query FFN and the pixel FFN. That FFN is stand for the feed-forward networks. In the query FFN, it had 2-layer MLP, and in the pixel FFN have 3x3 convolution. And in query FFN will have a layer normalization, and both of them is using the ReLU activate function. And in the previous mention that the after the pixel FFN and the query FFN, we will obtain RL and XL, and it will be input again to the same structure as the previous. So we will have several stage, and finally the will generate to obtain readout, and finally use the decoder to obtain the final result, which like this, that the mask of the cat in foreground and the background. And the decoder is also modified by the X memory. Okay, and next part is the experiment that author provide. That this, as we can see, that above is the traditional system, and we can see that the QT that is author provide, it have a much higher score than the previous and than above, and there will be some data set that comparison, and all of them is the video data set. Okay, and this is the author that mentioned about the hyperparameter using, including the number of the transformer blocks. The author used 3, and the number of object queries, the author using 16, and something that the other, like mask attention or not mask. And as we can see, the final result, we can see the author is using 3 transformer blocks, right? So this is generated after the first block, second block, and the third block, and the final block. So we can see that the final block is much clearer than the first block, and that is tracking the cat over here that is separate from the background. Okay, and this is the author provide the example. As we can see, the example here, this set, for example, as we can see that without the QT model, the model will some distractor over here, that the background that's what we don't need it, right? So the provide the Qt model will focus on the foreground and extract from foreground and without ignore all of background features. Okay, and that's my presentation. And thank you for listening. And Happy New Year. Thank you.